I'm going to present our work, Causal Transportability for Visual Recognition. Existing image classifiers achieve high accuracy on in-distribution data. However, they often fail on out-of-distribution samples. This is because models learn dataset spurious correlations that are not generalized to new environment. Causal transportability has been studied in causal inference literature. In computer vision literature, many work has been done to learn models that can generalize to new domain. In this paper, we investigate out-of-distribution generalization through the lens of causality, where we introduce the first analysis and algorithm of transportability in image recognition. We start by introducing the causal model. We assume there are nuisance factors UX, such as a water background and a land background, and the concept factors UXY, such as bird's flipper and beak. We encode our domain knowledge of visual recognition in this causal graph. The image X are constructed from concept UXY and the nuisance factors UX through a function defined by a switch node S. The ground truth label Y is affected by both the concept factors and the image we perceive. On the training set, the S variable is set to train, which makes the image construction function often selects water bird with a water background. An image classifier trained on this dataset will learn to use both foreground and background to predict the label. However, on the test set, S is different. The image construction function often selects water bird with a land background. The classifier that relies on the background information for prediction will fail. The association of image and the label between the training and the testing are different. To generalize, our model need to capture the invariant signal from training environment to testing environment. If we were able to knock off the incoming edges to X in the causal graph, then the correlation between the image X and the label Y will no longer be affected by the switch node S, producing a signal that is transportable across environments, which is a causal effect. To get the causal effect, one straightforward way is to conduct real-world experiments by actively intervening on the image X. However, existing datasets are passively collected. Our goal is to estimate the causal effect from only passive data. Unfortunately, we cannot estimate the causal effect from observational data in this causal graph. This is because we can find two models that generate the same observational distribution but have different causal effect. To identify the causal effect, we need additional assumptions about the data. Our model assumes the image is constructed from spurious variables W that contains background image patches, and the W then forms a shape Z that causes the image category Y. The representation in a deep model is used as a proxy similar to the front-door variable, which allows us to estimate the causal effect from observational data with the following estimator and assumptions that can be empirically satisfied. Here's the algorithm we use in learning and evaluating the model. On both simulated and real-world dataset, our method achieves better generalization on auto-distribution test set than standard empirical risk minimization method. We also study the importance of following our causal estimator, which marginalizes over random sampled images. The more data we sample, the higher generalization performance we have. We also use GradCam to visualize the regions that contribute to the prediction of the model. While baselines use spurious correlations such as a background for prediction, our method uses the right foreground for prediction. To conclude, we use causal transportability theory to revisit and formulate the problem of out-of-distribution classification. Our findings suggest that integrating the causal knowledge with the right assumption can improve generalization.